Hello and welcome back. In this particular video, we're going to unpick where the conditional probability formula comes from. We're going to use a tree diagram to explain that, and then I'm going to talk a little bit about how we can unpick that a little bit more inside of a question where it's really useful to go and use it, where it's not easy to go and use tools like Venn diagrams and tree diagrams and all of that sort of stuff to help us. It's just quicker and easier to go and use the formula. Now, um, essentially, when we're thinking about conditional probability, we're talking almost entirely about uh, dependent events. So, as in the previous event will depend on the first one. A great example to go and have a little bit of a look at this is tree diagrams without replacement. Okay. So let's draw a tree diagram to go and actually represent this problem, and then we'll use it to unpack the formula. Now, we have three red balls and we have two blue balls that are in a bag. So drawing that, you'll notice that we have in our first draw, no matter what, two outcomes. We have a red and a blue, and we have five total possibilities inside of the bag, of which three of them are red and two of them will be blue. Remembering that we know that our probability tree is correct if the branches in each individual section add to one. Now, the next part of our statement says a ball is taken from the bag without replacement. Okay. Which means we don't put the ball back in after our first draw that's happened here, and then we take the second. So this is what happens in our first draw. We don't replace it, and then we put a second ball back in. So you'll notice that we will still have um, both red and blue outcomes in there. However, the probabilities are going to change ever so slightly. So unpacking this, what will happen now? We've already taken a ball out, so we're going to be left with four balls inside of the bag after the red draw. From the red draw, you'll notice I initially had three. Because I've drawn one of the reds out while I go along this branch, I'm now only going to have two. However, I haven't touched the blue outcomes, which means I'm still going to have two blue left inside of the bag. Going the other way, I'm still going to have four outcomes once I reach here because again, it's without replacement. However, this time I've taken one of the blue balls out, which means I'm left with a 1 in 4 there. In this particular example, going down this branch and here, I haven't touched the red balls, which means I'm still left with 3. So I'm going to have 3 out of 4. You'll know you've done this correctly when you're doing a without replacement problem if the numerator has decreased and you have adjusted dependent on the branch, i.e., this is a dependent event. So dependent on the first draw will it impact the probability of the second. And like before, if you look at the fact that each of your probabilities inside of your branch segments add to 1. So 2 over 4 plus 2 over 4 is equal to 1. 3 over 4 plus 1 over 4 is equal to 1. Okay? Alrighty. Now, let's unpack this a little bit more so we can actually see what's going on. First and foremost, what I want you to understand is the fact that on our first draw in this particular section here, this is essentially just the probability of drawing a red in the first turn. Okay. Once I go along this particular branch here, let's just have a look at this one in particular. I might highlight it so we can see what we're working with. Once I go along that particular secondary branch, this is the probability once I reach along here of drawing a blue, and let's put this in probability notation, drawing a blue given that I have already drawn a red. So you'll notice as I go along this branch, the probability of drawing a blue given that I've drawn a red is 2 out of 4. Down here, the probability of drawing a blue given that I have already drawn a blue is 1 in 4. Okay, so it's a dependent event. And you'll notice in probability when we go along the branches we multiply, we've talked about that a little bit. The overall probability that you would get from this branch is essentially through multiplying. So this is a probability of getting a blue and a red. It doesn't really matter in terms of the order of the intersection because we can write them both ways, but we'll say a red and a blue for this particular one. Independent events. So, sorry, I should specify that. In dependent events, it's not like independent events that don't have any impact on each other. The formula for calculating the probability for this particular one can be calculated like this. The fact that as we go along the branch, we're going to use that probability, which is P of R, multiplied by that probability, which is P of B given R, and that's going to give us our resultant probability overall. So we end up with this. The probability of a red and a blue is equal to the probability of red times the probability of blue, given that a red has already occurred. Okay, now we can actually do a little bit of adjusting here to isolate our conditional formula. Okay, I'm going to divide by the probability of red over to the other side. Okay, that means I'm going to take this and do a division, and I end up with this. And you'll see we end up with the fact that the probability of blue, given that a red has occurred, is equal to the probability of red and blue divided by the probability of red. If you think back to our Venn diagram example, I told you to look out for where we're going to see the intersection over the restricted sample space. Okay, we can see that coming to life in this particular example. So, putting it all together now, basically it means we have this particular formula. You can see this structure almost always happens, which gives us the probability of A given B is equal to the probability of the intersection of A and B divided by the probability of B. So we restrict the sample space to B having already occurred. And then we look at all of the outcomes that are in both, like what was happening with that Venn diagram. Something that is worthwhile noting, whatever the letter is that is in the given statement, i.e. the B, that will always go on the bottom. Okay, so if you're struggling to remember where everything goes in this formula, because it's a little bit complicated, okay, you'll end up remember it if you just remember that that goes to the bottom. Something worthwhile noting, this is only independent problems. So in a dependent problem. Now, if we have an independent problem, the formula for this will change slightly, and we'll see that a little bit later on. Okay? Alrighty, let's use this inside of an example. So, Lara is an athlete who enters a swimming and a running race. So, swimming and running are going to be our events. She has a 44% chance of winning the swimming race, okay, and a 37% chance of winning both. Now, that means for winning both races, that is swimming and running, noticing my notation there, it's a 37% chance, okay, or 0.37 in a decimal. For winning the swimming race, okay, so that's swimming, all right, it is a 44% chance or 0.44 as a decimal. Now, looking at the rest of the question, we're going to find to the nearest whole percentage the probability that she wins the running race if she has won the swimming race. So, the probability that she wins the running race given she has won the swimming race. Using our conditional probability formula, we know the probability of winning the race, the running race and the swimming race divided by the probability of swimming is the formula. Again, seeing that note of the fact that the S is going on the bottom here. Now, because there's no easy way to necessarily go and represent this inside of a Venn diagram, we're just using the formula to make our life a little bit easier. All right, now we can begin to calculate it. Oh, sorry, my apologies. The probability of R and S, which is 37%, is 0.37, divided by the probability of her winning the swimming race, which is on the bottom there, which is 0.44. Putting that into our calculator, okay, you'll notice, and I'm not going to the nearest whole percentage here, I'm just going to the fraction, just so you can see what's happening, is 37 over 44. Okay, putting that in as a percentage is not too hard. You take it and multiply it by 100, and you'll get the full answer that we're after. I'm more so interested in terms of showing you how we structure a question like this. Okay, all right. Thank you very much. In our next couple of videos, we'll talk a little bit about using conditional probability with tree diagrams. And then we'll talk about using conditional probability with two-way tables. Okay, thanks very much.